Hello, my name is Kevin Duke and I'm an analog applications engineer here at Texas Instruments. Today we're going to look at how to design protection circuits for analog I/O modules. This video assumes basic knowledge of common transient signals, the IEC 61000-4 certification suite, and the corresponding IEC 61000-4 test signals. For full review of this material, check out my other Engineer It video that explains analog transients and IC damage. To find it, search for Engineer It Introducing Transient Immunity for Analog I/O. IEC tests replicate real-world transient events that are high voltage and high frequency signals with potential for large current. These signals may be repeated, so the circuit must be robust enough to survive multiple strikes without permanent damage. The two basic strategies we'll employ to protect our system are attenuation and diversion. These strategies will take advantage of two properties consistent across all of the IEC 61000 transients: their high frequency component and their high voltage component. Attenuation uses passive components like resistors, capacitors, and ferrite beads to attenuate high frequency changes and to limit current. The level of effectiveness depends on our ability to anticipate the input signal's shape, magnitude, and frequency. Diversion capitalizes on the high voltage properties of the transient signal by using diodes to clamp the transient to ground and divert energy away from the rest of the system. When used individually, both of these strategies will have drawbacks, but when used together, they can create a very robust solution. We'll go through a series of examples using the OPA 333, a 1.8 volt zero drift op-amp. Attenuation with a series resistance alone is a simple and inexpensive way to reduce the current going into your IC. It will not, however, attenuate the voltage going into the IC and can add an offset voltage via Ohm's law. If we add a capacitor to the scheme, we've created an RC filter. Just like the simple resistor solution, we've reduced the current going into the IC, but we've also added frequency-based voltage attenuation to the mix, reducing the volume of energy the ESD cells internal to our IC may be exposed to during a transient. Remember that the level of attenuation from the RC filter is dependent upon the input signal's frequency and shape. For example, let's use a 1 kilo ohm resistor and a 0.15 microfarad capacitor. Using F equals 1 over 2 pi RC, we can calculate that a 1.06 kilohertz signal will see 3 dB of attenuation using this combination. If we drop the circuit into T/Ti, we can graph the frequency response of the RC filter and confirm 3 dB of attenuation at around 1 kilohertz. To confirm the RC filter in the time domain, it's convenient to run transient analysis on a 10 kilohertz sinusoid that should be attenuated by 20 dB, or exactly 1/10. As you can see in this slide, the T/Ti simulation confirms our expectations. The transients we need to protect our circuit from aren't perfect sinusoids though. They're closer to impulse signals. What happens to the RC filter if we apply a square wave instead of a sinusoid? This time, the transient simulation shows the 10 volt peak-to-peak signal attenuated to 3 volts peak-to-peak instead of 2 volts. Foregoing all the mathematical details, this is because the impulse signal in the square wave creates higher frequency content than the sinusoid. For impulse signals, it is more appropriate to size RC combinations using F equals 1.5 divided by 2 pi RC to realize the desired cutoff frequency. You can think of ferrite beads as resistors whose impedance at DC is near zero, but very high for high-frequency signals. Replacing the resistor and the RC filter with a ferrite maintains DC accuracy while delivering current and voltage attenuation to high-frequency signals. In summary, remember that the effectiveness of attenuation depends on the frequency and shape of the disturbance. The transients we're protecting against can be high-power signals, so the passive components with sufficient power rating will be quite large and increase solution size. Finally, remember that the use of ferrites can deliver attenuation without sacrificing DC accuracy. The diode is the centerpiece for the diversion strategy. Specifically, we'll use the TVS diode or avalanche diode and the Schottky diode. The TVS diode is optimized for quick reaction to overvoltage and for passing large transient signals like ESD. The Schottky diode, meanwhile, has very low forward voltage drop, usually 150 to 450 millivolts, which will help ensure that during a transient event, the IC's I/O lines are kept within their absolute maximum ratings, which are typically 300 millivolts above and below their supply rails. Placing a unidirectional TVS diode alone in the protection circuit will limit the voltage at the input based on the diode's breakdown voltage. This is a very simple solution, but it will only clamp positive voltages. Conveniently, manufacturers also create bidirectional TVS diodes, as shown in the schematic on this slide. The bidirectional TVS diode will limit the voltage based on the diode's breakdown voltage, just like the unidirectional TVS diode, but it will suppress both positive and negative signals. A downside to this strategy is that the breakdown voltage for a diode increases as the current flowing through the diode increases, and this scheme alone has no way of limiting current. Bidirectional TVS diodes can be helpful, but most have symmetrical breakdown voltages, so systems with non-symmetrical supply rails will have to use two unidirectional TVS diodes. If you combine attenuation and diversion strategies, a very robust solution is realized. The transient signal first encounters the FBC filter, where high-frequency voltage is attenuated and high-frequency current is reduced. If the transient is still of sufficient magnitude following the FBC filter, the bidirectional TVS diode will quickly clamp the transient signal to ground. But it could be less effective if there is still a lot of current flowing from the transient signal. To fix this, a small pass resistor can be put in place to limit current, followed by a pair of Schottky diodes that will clamp the I/O lines to the supply rails and within the absolute maximum ratings of the IC. So in designing your next analog input or output module's protection circuit, use both attenuation and diversion to provide the most robust protection. Remember that attenuation is dependent on both signal shape and frequency. Use ferrite beads to limit and attenuate high-frequency components while maintaining DC accuracy, and TVS diodes to divert large voltages. If you expect high current signals, remember that the TVS diode breakdown voltage will increase, and it may be necessary to add a pass element and a Schottky diode to clamp to the rails. For more information, please visit the following URLs.